And then he was like, well, do you join the group? I was like, oh, I didn't even know the group existed. And I went to the web page and then browsed through, and there was some really good presentations and stuff. So, and then he did ask me if I could do some sort of presentation. That was kind of quick, though. It was just last week, right?
Yes.
It was just last week, and I've been thinking of doing this, this kind of talk, especially just because there's been a lot of changes in the way statistics and the analytics world is moving towards, and it's just very latest, very trendy. And I thought, and I've been thinking of doing this for a different audience, but this will probably be like a pilot, and I can gather feedback from you guys and make this a little bit better. Okay. All right. So today, what we're going to do is to talk about contemporary developments in good statistical practices. So I'm not going to get too technical in this, but it's going to be a little bit of it will involve a little bit of technical aspects to it, but on a surface level, like what Nick showed you guys was perfect. Kind of a perfect setting, doing a regression or a t-test or whatever you've done before, and getting a p-value and all that. So, end of the session, I would like for you to take home your take-home message to be that, okay, this is what it was done in the past, but what can we do better, and how the trends are changing, and what needs to be done better in the future. So that's the goal. And like I said, it can get really technical, but I'm not going to get into the technical aspects of it. But if you do, I am actually going to send Nick a folder full of different articles that are published, and you can always refer to that. And I'll kind of refer to that back and forth as we move on. All right. All right, so agenda, I'm going to take you back to the first class stats course for a second, for a few minutes, and it's going to involve hypothesis testing. And with a simple example, and we already kind of did that. Nick showed us that, and then we're going to talk about p-values, right? So that's one thing that we always have seen in every stats course or any kind of analytics that we do. Usually, we end up with the p-value. We'll talk about an example, and then a brief history of p-value. How did the p-value actually come along? And then we'll talk something about p-hacking. How can you hack p, which is not good. Anyways, and then we'll get into the articles that have been talking about these significance levels and all that, and then we'll talk about the latest statement from the American Statistical Society about how to do practices better, and finally, I'm going to discuss a little bit on the p-value revolution, and then finally, good statistical practices. So the last two slides are going to be like your pointers to where what needs to be done when you do your own data analysis. I know people from different backgrounds, and then especially the analytics world, and then the BI, business intelligence, and all that. But trust me, the foundations for everything is statistics. So this is the foundation. So that being said, let's move along. And if you don't understand something, please, you're more than welcome to stop me and ask me any questions anytime. And let's see. Let's go back to the first stats course for a second here. So everybody knows this, but this has to be said. So types of variables, we have quantitative variables and we have categorical variables. And then quantitative variables, we have summary statistics, like the example that Nick showed us was we had two quantitative variables there, right? So we had the height and the weight, and then we had a categorical variable, which was the gender, male and the female. So how can you summarize it? So we can summarize it using mean, median, mode, maximum value, and then the interquartile ranges for the quantitative variables. And for the categorical variables, it's pretty simple. So what percent of males are there, what percent of females? So, and then an important aspect of everything is going to be population and sample. So these are the two terminologies that pretty much drive every statistical formula. Okay. So what is population? Population is everything under study that you have, and the sample is a teeny bit of it. So, for example, let's just say you're doing a study. The study is about, say, you're trying to see employee satisfaction in your company, and let's say you have about 25,000 employees in your company. I think UAB has about 25,000 employees at this point. So if you want to do a satisfaction survey, would you go and give the survey out to every person? Naturally not, right? So you do a sample. So would you give it to 100 people? Maybe 100 people are not enough, right? So you've got to have the right sample so that you're not going to have a biased conclusion. So So this is the driving aspect of it. So I'm going to come back to this back and forth. So let's just say population is this, whatever study you're doing, right? And then you always take this teeny bit of it, sample. But this, you pull it out and do that data analysis on this. Of course, we're not really talking about data mining or big data and all that right now. This is just the foundations. So we always take this little sample and then we refer back to population. So for example, I think I read this the other day. It said something like 1 in 5 relationships are made online. Is that a true statement? Probably more, probably less. We don't know. But they never talk about the samples. Or I saw another stat that said 40% of Americans are meeting people online or something like that. Or relationships are made online. Okay, they never refer anything to the sample, right? So same thing goes with, when you see these ads on TV about, okay, the vehicle mileage was so and so. They didn't go and test out every vehicle. They took a sample of it. But the deal is you always go back and refer to the population. So you're making inferences back to the population from the small sample. Okay? Let's remember that. That's exactly what we're doing. And that's exactly what you're seeing everywhere. Nobody's really tested out the population as a whole. But you can already see the problems with it, right? Think about it. Bias sampling. That happens all the time. And you can set up your samples however you want. Okay? So that being said, let's move on. How many of you have heard of hypothesis testing? First stats course, everybody has at some point, right? So what is it really? And we'll come back to the next example. Actually, it's perfect setting, by the way. So let's just look at what is hypothesis testing. Let's look at a court case. So what happens in a court case? So innocent until proven guilty, right? That's the deal with the court. So we have 2 types of hypothesis. So the first hypothesis is the null hypothesis. The null hypothesis pretty much says the defendant is innocent unless he's proven guilty, right? The defendant is innocent. And then the alternative hypothesis is going to be exactly opposite usually. So that's how you set your studies up. Any study that you see, that's how it's set up. So, and every decision that's made, or the final decision that's made by the judge, is based on the data that the judge gets, right? So the data comes from everywhere. And then the judge looks at it, the jury looks at it, they analyze it. So it's the same process that goes on even in statistics, in the statistical world. So you can either reject innocence or you don't reject innocence. So when you reject innocence, what happens is you declare guilty and the person goes to jail. And when you do not reject innocence, you don't declare not guilty and the person goes free. Which one's worse? Right. So that's a good question. So we always have to keep that in mind whenever we do. So we'll come back to that. That's all right. So, oops. Okay. So we can make errors in the decision, right? So I think you've heard of this, right, before, type 1 error and type 2 error in your classes. So type 1 error is concluding that the hypothesized parameter value is wrong, but in reality it is correct. So basically you can make so what it is saying is you're wrongly proven this wrong. Meaning, I'm going to write this. So H naught is going to be your null hypothesis. So you're actually rejecting the null hypothesis. In reality, it is actually true. So that's one of the errors you can make. And then the type 2 error is exactly opposite of this. So there comes the alpha value. So what is alpha? What's the number you've seen that goes with alpha? 0.05, right? 0.05, the standard of it. So that is the level of risk chosen by the user for allowing a type 1 error to occur. So that's usually 0.05, then that's what you've seen. Sometimes it's 0.10 or 0.001, whatever, right? Okay. Now, let's look at an example. Let's look at our own example. So, going back to the sample and the population. So, let's just say we have actually I own a chips factory. I make chips. And then I make chips of different sizes. Chip bags are different sizes. Let's just say one of the chips bag I make is 16 ounces. And one of you is an FDA inspector. So you show up to my factory to check if I'm actually doing the right thing, meaning bagging all the chips to be 16 ounces. So as an FDA inspector, you need to hypothesize this, right? First of all, your hypothesis, your null hypothesis as an FDA inspector would be H naught I'm making is equal, or whatever, the sample mean is, or let's just say 16 ounces for now, okay? So what do? You come to my factory, and then obviously I'm making 10,000 bags of chips. You're not going to take each one of them and weigh them, right? So you're going to take a sample. You will take a sufficient sample, pull it out of here, and then weigh them. And then after you do that, you will find the average, right? But what you had said your hypothesis was to be 16 ounces right here. So you're either going to reject the fact or accept the fact. So as an FDA inspector, you don't mind if it's greater than 16 ounces, correct? But what would be the problem is if it's less than 16 ounces, because you're cheating. If it's going to be greater than 16 ounces, I'm the one who's under loss as a company. So that is what we call the hypothesis testing. So any study you do is going to be based off of this sample and population idea. So take the sample, and then I hypothesize my study first. So my hypothesis here is the fact that it is going to be, I'm just going to say greater than or equal to 16 ounces from the FDA's perspective, right? And anything less than that is going to be what we call the alternative hypothesis. So these are the two hypotheses, and we always use this for any statistical test that you have done so far. So in the example that Nick showed us, he talked about a few things there, right? The p-values. There were 3 different p-values that was generated. As you can see, there was one p-value with the f-test on the curve. We'll go back and see that in a minute. And then there were 3 p-values. One was for the height, weight, and the random variable, right? So there were 3 p-values that were generated. All three of those are 3 different tests. They have their own hypotheses, and the p-values are generated based on the hypothesis of the same idea. In that case, what you didn't notice, again, I'm going to go back to that, is the fact that the p-values were based off of something called a coefficient. There were numbers that was like 0.01 and so on, right? For the first column was coefficients. So based on the coefficients, the p-values were generated. Okay? All right. So now we know that any kind of statistical test that you see that generates a p-value will have a hypothesis test behind it. And these hypothesis tests are all kind of preconceived, meaning they're all mathematical. So they have what we call mathematical models behind it, and that's how they're generated. Okay? All right. So we talk about the type 1 and the type 2 error. So type 1 error is going to be penalizing the potato chip company when in reality they were not cheating the consumer. Type 2 error, not detecting the potato chip company was cheating when in reality they were. Which one's worse from the FDA's perspective, at least? 2, right? Type 2 error is worse from the FDA's perspective. So really, the errors really depend on the study and who's doing the study, what type of study. Okay? So that's another point just to know. Okay, now we go to p-values. I know a lot of you, I was talking to Nick earlier. Nick was like, oh, I'm scared of p-values, right? So can anybody just tell me what, in your sense, what is a p-value? I'm pretty sure you've used it at some point.
The likelihood that the results were due to chance.
Okay, those are good words. Yeah, absolutely. Anything else? And then you always compare p-value with a standard value, which is alpha 0.05, and you either reject or fail to reject your hypothesis, right? All right, so let's write this down now. P-values. Informally, a p-value is a probability under a specified statistical model that a statistical summary of the data, example, the sample mean difference between 2 compared groups would be equal or more extreme than its observed value. Okay, I'm going to write this down in just symbols. So it is the probability, okay, that let's just say, in this case, then how many of you know a z-table, right? Bell curve. Everybody knows about a bell curve, right? So let's just say a bell curve of 2.8 or something greater than the, oops, not this, p z greater than 2.81 given the null hypothesis is true. I know this is probably a little pz greater than a value, a z value, given the null hypothesis is true. That's the actual definition. So we'll go back and forth with that with different examples, but just so know that every test that you generate, the p-value is based off of this right here. This is like the standard formula. The z changes to different distributions because based on the kind of test you're doing, the z, it can be a z test, it can be a t test, and it can be a chi-square test, right? You've heard of a chi-square test also, given the null hypothesis. So that is the actual kind of informal definition of the p-values, okay? So it's not that hard, really. Once we look at an example, we'll know. Okay. A low enough p-value says the data we have observed would be very unlikely if our null hypothesis were true. So if we have a low value, which means to say that we'll have unlikely that null hypothesis was true. So if you believe in data more than assumption, then you'll see a low p-value. Then you should reject the null hypothesis. So let's keep that standard still. So basically, let's just say if our p-value is less than 0.05, we are going to go ahead and reject the null hypothesis. Okay? All right. So I think I want to go ahead and like bring up the example here. Okay? So the next one is going to be a table which some of you have probably seen this table, some of you have not. Okay. So all your p-values actually come from tables like this. So I'm pretty sure in one of your stats courses where your professor made you calculate the p-values and look at these tables and you wrote this down, right? You wrote the probability. So these are all probability values right here. So what is this saying? So this is just the standard normal distribution. So the bell-shaped curve that everybody has kind of seen before. Okay. All right. Can everybody see this? I think so. All right. That'll work. So bell-shaped curve. So in the bell-shaped curve, what is this? How do you get this bell-shaped curve to begin with?
Pretty much never.
Never. Absolutely. That is why it is a model. No, you're right. You're absolutely right. You never get it because this is a model, right? This is a statistical mathematical model. You'll never get it like this. But how do you get this? So this is nothing but, let's just say weight, okay? Let's just say weight, and then you draw a histogram of weight. So histogram of weight will look like this, whatever. So eventually, if you have enough data, and if you draw a smooth line to this histogram, it becomes a bell-shaped curve like this. Okay, this is the origin of it. So in a standard normal distribution, meaning it has certain mathematical properties, and it's like the standard. Let's just say it's a standard. So in the center of it, it's going to be the mean of it is 0. Okay, and then as we move forward, the standard deviation is going to be 1, 2, and 3, like positive 1, 2, and 3, and then this side is going to be negative 1, 2, and 3. Trust me, this is kind of important to where we're getting to. Okay, so when you look at the table, let's look at the first value on the table. It says 0, z, right? Z 0, 0, right? What is it? It says 50% or 0.50. First value, 0 and 0, right here. So what does it say? So what it's saying is, it's saying all the way from here to the center of the curve, it's 50%, or the probability is 50%. So, and as we move on, it's going to get higher. So let's look at 1. So 1.0, it's 84 or 0.84 or 84.1%. So right here, if I draw a line, all this area, it's 84%. And then at 2, look, what happens at 2? It's 97% already. So at 2, it's going to be 97. And at 3, it's almost a 1, so it's 100%. So the first curve that you saw in Nick's example, one of the F tests, it had a tail ending like this, and it had a dark shaded area, right? So going back to our definition of the p-value, to actually do p-values by hand, this is how it goes. So once you calculate your own z-score, then let's just say your z-score was 2 or 2.81. So if it's 2.81, it's kind of close to 3, right? So any value that's greater than 2.81, and given the null hypothesis is true, this is that value. It's a very small value, so that's good. That's why you'll end up getting a very small p-value, which is going to be 0.001 or something. Okay? So every test, like the one that in regression that we saw, it had an F test. So F distribution does not look like this. It has a tail that comes down like this, right? So that's a different distribution because that's how it is. And then we have different kinds of distributions, and any distribution, anything. In any case, this is the standard formula. The z changes to maybe chi-square. The z changes to maybe an F test, and so on and so forth. So this is how the p-values are calculated. And remember, these curves are all standard. So that is, like I said, there's a mathematical formula behind this, and then all these probabilities are calculated based on this formula. So this is just a p-value. That's it. Okay? So thank you. Get a sense of a p-value? Okay, so this is going to be the next part of it is going to be really interesting then. So now we all kind of have an idea what p-value is. That's all. That is exactly what a p-value is, and that's it. All right, so here's an interesting history. And then, how many of you know, so there's another test that compares two groups, right? T-test. I think some people have used t-test before, like you say males versus females, we could use to compare the heights and weights and whatnot, right? When you have two groups, you can use a t-test to compare. So the t-test, how did it come by? This is going to be interesting. So the head brewer of the Guinness brewery in Dublin, Ireland, needed a new statistical model because whatever he was using was not working. So the normal distribution that you saw was not working with whatever cases he was doing. So what he was trying to do was just trying to see if so what are the best varieties of barleys and hops for brewing, right? And then how should they be grown, dried, and stored? Basically, he was trying to optimize the whole entire process. So what he did was he actually came up with the t-test in a brewery. And he couldn't publish the results because it was all proprietary stuff, and he had to go through a different name. So he had a pseudonym. He started publishing all this stuff under pseudonym. That pseudonym was called Student's T-Test. So that is why the Student's T-Test. And then I think there's another story behind why it was Student's T-Test, because I think he liked one of the hops or something. The hops were called Student something. And then so he used that pseudonym to start publishing. So this is also a little important to where we're actually going. All right. Now this is going to be a little fun. P-value misuse, aka p-hacking. So this has been going on for years and years and years, and knowingly and unknowingly, because of the way things are. So p-hacking is also known as data dredging, snooping, phishing, significance chasing, and double dipping. So these are all different words that have been used. And what does that mean? So when you want to find significance, you can find it. When you're going after just the fact that you want your p-value to be less than a certain number, which is 0.05, right, the standard, you can do it. There are several different ways to do it. So you can cut off the variables. You can use only certain variables. You can cut off the data points. And people have done it before. Okay? So there is a really cool article which I'm going to show here. How many people know 538 website? It's really cool, right? And there was an article. This was published a few years ago. And all right, Nick, I might need. Okay, I think I should be able to do that. There. All right, this is a really, really cool article. Has anybody read this article before? It's really cool. So Nate Silver runs the 538. So he was the guy who actually predicted the 2008 elections pretty accurately, but they didn't do a good job with the last elections, though. So in terms of predictions. So this article pretty much talks about how people have been hacking the p-value. Okay, so this is pretty dynamic where we can change things. So let's kind of look at this really quickly here. So you're a social scientist, and the U.S. economy is affected by whether Republicans or Democrats are in office. Try to show that a connection exists using real data going back to 1948. For results to be publishable in an academic journal, you'll need to prove that they're statistically significant by achieving a low p-value. So let's play with it for a second. So let's go ahead and choose a political party. Let's just stick with whatever we have here. So, okay, so let's say Democrats. And then we're going to choose senators and representatives right here. And then how do you want to measure your economic performance? Let's just say stock prices. I'm going to get rid of everything else. Do you see how the p-value is fluctuating on the right? See, this is the p-value. So if I take off employment or GDP and inflation, your p-value gets higher. It's 0.19. So this is how you can hack your way basically to a value that however or whatever you want it. And there has been, if not thousands of articles that have been published that are wrong just because of the fact that they've done this before. And a lot of times, and this is what we're actually going to get into, and how not to do it, and what's the better way to do it, right? So as you can see, just in this, the p-value just changes. I'm just going to click on inflation. Look, if you just add inflation to it, it changes. So what does it tell you? So every study that you actually see these days, you need to be careful to see how it was conducted to begin with. Where did the data come from? What are the variables? Those are the most important things. And a lot of times, they're not transparent. You don't know where it is, right? I mean, that's another thing that you need to be like really, really careful about also. So let's say we change this to Republicans and see what happens. Well, it changed a little bit. So let's just say I'm going to add governors. Didn't change much. Look, I changed the p-value. It actually got a little higher. Okay. So this is a cool article. So you definitely need to probably read it. Another thing that they did was some of the researchers did this. This is a really cool study that they did. So same data sets. 29 research teams were given the same set of soccer data and asked to determine if referees are more likely to give red cards to dark-skinned players. These are like 29 different researchers with same exact data sets. Each team used a different statistical method, and each found a different relationship between skin color and red cards. Look at this. So these are all non-significant results, and the ones in green are all significant results. And look how different they are. So you would say, go on.
Curious, like as a layperson, you just start to wonder if this is all bullshit.
Absolutely.
Yeah, I'm serious.
Yeah, no, you are.
And how do you sort out like what's good or not, right? Because like a regular person can't.
That's exactly. That's an excellent point. You're absolutely. So that's exactly what we're trying to go towards. Like, okay, what are the things that we need to look for when we look at studies, or when we have our own studies, or when we have our own data to do in terms of the analysis plan, and you have to be comprehensive in your analysis. A good way to look at it right here is people use different statistical techniques. Your conclusions can also be based off of different techniques. Not only the way you're doing it, but your statistical tests. And I always say this, and I've worked on different projects and different data sets in the past, and it's so overwhelming that you can actually do the same thing in different ways. It's like, okay, I want to get from point A to point B. Yes, you can go like this, you can go like that. There's different ways to get there. There's no one specific way, but it has to be a logical way to get there also, right? So Sure.
Another layperson. So I just had a conversation on the way in of someone with a buddy of mine that math is absolute, 5 plus 5 always has to equal 10. With statistics, if somebody's taking a different approach, is it absolute that they should always come to the same exact conclusion, right? Or am I wrong?
No. Conclusion is different. They should. If they do come to, they should usually come to the same conclusion whether they're doing it. If they're close, sure. But transparency is what should matter there. So they should say, okay, we use this technique and we use this also. Just to say that both are given different techniques, I think the conclusion should be both are given different conclusions. There shouldn't be one conclusion.
So regardless of technique, they should come to the same answer.
Depends. Depends on the problem in hand. That's exactly what I'm saying. It really depends on the problem in hand.
This is a very useful tool because, like, I think of analytics in 2 ways.
Mm-hmm.
One is like we try to answer questions we can figure out what the truth is.
Mm-hmm.
The other one is we already have decided what we want to see.
There we go. Right.
We're looking for data to support our story.
Absolutely. So,
The business world is really like.
so yeah. Mm-hmm.
Explain. I'm struggling here a little bit with what we're looking at.
Mm-hmm.
So 2019, we're given the same data,
Mm-hmm.
and they came up with different probabilities that the referee is biased. And so the first thing that I find striking is your first data point says they were biased toward, well, they gave more cards to white people.
So,
The rest of the data says, no, they gave more cards to black people.
so this equally likely are probabilities. So it depends on the kind of statistical test that you're using, and how the data was massaged to begin with, and how it was applied to a certain statistical formula also matters. So these are the final conclusions based on just significance and not significant, which shouldn't be the case, right? So we have about, let's see, how many do we have? So we have these to be non-significant, but this to be significant already, but they're equally likely. So how is that possible? So there's more than one way to analyze things, and you might end up getting several different results, is what you're saying. Uh-huh.
Yeah, I just want to point out one more humbling moment that I had in that conversation with Carl and I came over is that I saw a buddy of mine that, we present this data and this analytics and these charts and these graphs and we're like, how can these end users not get it? They got to be stupid, they got to be idiots. Like, I did all the math for them, I did all this work. But even in this audience, now you're like, we're confused. And so now you can understand how business leaders will sometimes go with their emotions as opposed to going with the logic and the data that presented so they don't get to like, this guy treats me better, so I'll go with that.
Right, right. So the final conclusions are always kind of, it depends on a lot of different variables. And also, what we don't really see here also is, yes, the green, cards that were given, and also there was a lot of different variables associated with it. So it was a huge data set, right? It was just not, so the one before that, when we clicked on the variables that we use, it changed a little bit, right? The p-values changed. So that's what people are doing here also. So certain techniques, you can use certain variables. Sometimes you can use those. Sometimes you can't. So I would say it's an ocean. And people, the point is, not everything that you see and read and hear is always going to be right. Okay? So at least it gives you a sense of, okay, questioning. Where did the data come from? What are the variables? What was the technique involved in it? Things as such, right? And also, how many people know John Oliver here? Okay. John Oliver has a whole segment on this. Has anybody watched it? It is amazing. So that's one thing I also have right here, which I'm just gonna open this up really quick, and we don't have to watch it. You guys can watch it later. But this is one of my best videos that I usually use. This, if you don't like, oops, it's restricted for some reason.
That's probably our internet doing that.
Yeah, you can't have any fun at work.
Yeah.
Okay. Well, this is educational. Okay. So there is that video that it's really fun. It's about 20. Usually his videos are 20 minutes, but he covers a lot of different aspects and a lot of different studies that we just saw. How there's one study he talks about. Well, there's one study, or you probably read it before, that says, oh, drinking wine is really bad for you. The next thing you know, drinking wine is like really awesome for you, right? Which one to take? So he has his own ways to like talk about it, but I think that's going to be a really good video to watch. All right. Now, I want to refocus a little bit on how is analytics, right? Analytics, business intelligence, all these kind of words that awesome words that you hear, again, is all kind of based off of the foundations of mathematics and statistics. What's included, what's new to it, is the artificial intelligence or the computer science aspect to it. So back in the day, when we did analysis, we couldn't do analysis this fast, right? Because we didn't have powerful computers, and we didn't have computer science algorithms. But now we actually can. And actually, my focus and my expertise is on data mining and big data. And I do statistical modeling in using big data usually. But again, the key aspects is the foundations. You really have to know this to get there also. Like I mentioned, some of the formulas that we still use are still based off of some of this. It's been modified for big data, but we're still using those aspects of it. So that's why I want to focus a little bit on a brief history of how everything started. It wasn't too long ago. It was like, especially statistics. It was early 1920s. So the significance levels are the p-values that we see, and the bell-shaped curve was before this, but at least the significance levels and everything else was early 1920s, and it was started by this guy right here. His name is Ronald A. Fisher, and he did not mean it to be a definitive test. The way he put it, he intended it to be simply an informal way to judge whether evidence was significant or not. So how did everything change, and how do we start using p-values like crazy? Then what happened was, there were two guys that hated him, and they hated each other. So they came up with their own formulas and their own ways of doing things. So you guys have probably heard of Pearson, right? Pearson correlation test. The correlation test. So he was the one who coined that. So these two guys introduced an alternative framework for data analysis that includes statistical power, false positives, and all that. And they hated the idea of p-values. And then they started hating on each other, and this became a big deal back in the day. In the statistical world, they called each other all these names and all that. And then there were other people that were trying to publish what they were talking about, and they had no clue because they didn't have an idea what was going on. They started saying, oh, let's just use p-value as 0.05 because he used it. So that's how it started. So it was never meant to be used as 0.05 or significance testing. Okay? So you kind of get an idea of the history here. Now we'll focus on this. This is an article. It was published in 2005. Has anybody ever read this? So it says clearly why most published research findings are false. This is an excellent article. So why is it false? High rate of non-replication. So that's the key word. Meaning you cannot, some of these studies, you can't even replicate it again. So that's the whole point, right? You do a study of any sort, you should be able to replicate the study. So a lot of studies that were published were not replicable. So can you imagine how many studies in terms of at least like health sciences, right? That were all kind of wrong. So high rate of non-replication, lack of confirmation of research discoveries is a consequence that convenient yet ill-founded strategy. So the strategy was just to use that p less than 0.05. Okay, and this is also true. So in some of the softwares that you're using right now, there's a lot of softwares in the market, right? When you do some of these tests, it gives you some of the conclusions based on p equal to 0.05. So you need to be kind of careful about that. Especially there's like a lot of new products, I guess, these days. I can't even keep up with it in terms of like, BI tools and all that. So some of these tools still use these techniques. So at least it'll give you an idea, okay, I need to look for what the p-value is or how it is actually doing it. And also, if there's a financial, emphasis to all this, you start, getting the results that you want, basically. So this is a really good article that, that kind of started off the revolution on stop using the hypothesis testing and the 0.05 stuff here.
With that in mind, in your day job, when you're doing statistics, how do you address this? How do you run a model and you decide, yes, this is important, but then you have this fact you have up on the board. How do you control yourself so that you don't?
So in the next coming slides, I'm going to talk about that in terms of like, what are the things that you can comprehensively do to stop these biases? So, for example, one of the things I'm just going to say is, there has been a huge call for not even using p-values at all. Don't use the significance levels. So whenever you start comparing with 0.05, that's when you start making mistakes. So, and there are other ways of exploration. And then yes, if you use different techniques, you need to be transparent about it. Saying like, okay, I use this technique, this is what I found. I used this technique, this is what I found. I cannot conclude my entire results based on one technique and the way I did it, just because I wanted to get the answer there, right? So this is what we usually see.
So what happens when you're looking, you run these models or whatever, and you get to the point where one thing is telling you that this is significant or whatever, and then you run a different model for the same set of data, and you get a different answer? Like, how do you, what do you come to? How do you remove the bias from that? Oh, well, I'm just going to go with this versus that, or
yeah, it's an excellent question. So here, in the next slides, I'm going to talk about it. But no, it's good. But here, when we saw the potato chip company, right? So the first time when you collected the sample, let's just say you got 16.5. The next time you collected the sample, you got 17.5. So that's the nature of it. So when you're actually doing the analysis, again, transparency is important. So the first time I did it, so I got it. And also, there's a lot of aspects that go to it, right? So sampling. So first of all, you need to be the right. It needs to be the right representation of the population. So, for example, let's just say, again, going back to one of the examples I was talking about, which was satisfaction, employee satisfaction survey. Let's just say we have a company of 25,000 employees, and you go to one division that everybody's really happy, and you know they're happy there, and you just give out surveys just to those people. What do you think you're going to get? Bias, right? And then, you want to get bad results. You just go to employees that hate the company, and you go give them the survey. So yeah, representation. There's a lot of aspects to it when you're doing this study, yeah. So I have a list of things that. So those are my concluding slides, which we're going to talk about in a little bit.
Would you, like the employee survey, just off the top of my head, I'm thinking, would you do, if you get one, say you do two sample sets, you get two different results. One is unhappy, one is happy. Right? So would that tell you that I need to go get more sample data, that this is not, I don't have enough information here to give me a true answer?
Yeah, absolutely, yes. And then you have to be really transparent about it. You should completely say, I performed the survey on, say, 1,000 employees from this division at this time point and whatever happened around then, and then actually say the results, right? So instead of just throwing it out, oh, certain percent of my company employees are satisfied or not. So that explanation needs to be there. That's the most important thing. Okay. here, this is just one of the articles that actually just got published in Nature. And look at this. Let's look at the chart on the right. So we have 791 articles right here, and then wrong interpretations. Analysis of 791 articles across 5 different journals found that around half mistakenly assumed non-significant means no effect. So basic conclusions, like we were just talking about, are all wrong here. And false conclusions. Okay, and remember, going back to the example, the sample and the population. So what we're trying to do is this. So we're going back to this example right here, potato chips. So you got this, you had the whole company, that's your population under study, and you have a little sample that you took 1,000 or something, and then what you're always doing is you're taking this and making inferences back here. Meaning you're talking about the entire company and not ever about the sample, right? So every time you take a sample, it might vary a little bit. So you have to agree and accept on that. That's the nature of the beast. So what you're trying to do here is, when you say, this sample, say you got 16.5 ounces, you're going back and saying the entire population, or the population is 16.5 ounces. What you're doing is what we call a, let's see, where's the keyword here? Point estimate. So you're estimating the population under study from your sample, because you're making inferences back to the population, right? So you're making an estimation. So the estimation is the most important thing, and most people just forget that. So what does that mean also? So the effect size is also important, so which we're going to discuss. So as you can see in this case, the point estimate is really key, and then see how the non-significant, the same studies give non-significant values and the significant values. So what they're calling for is to forget the p-values overall. Like I said, these are all kind of really new. That's trends that are changing. And also, once you have like large sample sizes, p-value doesn't matter.
Let me see if I can repeat back what you said.
Mm-hmm.
I was having some concern about saying ignore the p-value. I think what you're saying is throw away the p-value if you give a range. So rather than say 16.5 ounces, what you're really doing is you're saying 16.2 to 16.8. That's what you're saying?
Those are confidence intervals, yes. So we can actually say that also. But making a final conclusion alone based on p-value is not a good way to go, because that's been the traditional trends. And like I said, a lot of softwares, a lot of research has been done on it, and softwares are still using the same kind of trends. But moving away from this trend is really kind of hard. So what can we do to comprehensively do everything right in terms of at least giving a big picture and clarify everything that we are trying to do, right? So that's what we're trying to do here. Okay, so this slide is more like the keyword I really like about this is embrace uncertainty. It's going to be uncertain. Your predictions, your point estimates, everything that you're doing, it's going to be uncertain. You're never going to be certain about it. So how do you deal with it? So, and you brought up a really excellent example there. It said rename confidence intervals as compatibility intervals. What does that mean? So going back to this example, so let's just say you took different samples at different times, right? And then you came up with a range for it. Instead of saying it's always going to be a 16.5 ounces, you can say it's going to range from, say, 15.5 to 16.5 ounces, right? Is that a little better? Instead of like actually pinpoint accurately saying, oh, this is what it's going to be. Well, we don't know. That's why it's between the two numbers. So that's good. That's good in a way. But traditionally also what's been done with this is, these are called confidence intervals, right? And then you can generate p-values for this also. But what you can do is you can take each value associated with it, meaning you can make predictions based on 15.5 and calculate a p-value. And 15 point for each, you can calculate a p-value for like each decimal point if you wanted to for that range, and see where it's falling. Okay, instead of traditionally, like I said, there's a lot of mathematics involved in it, by the way. So all the values between the interval limits are reasonably compatible with the data given the statistical assumptions, and also there's a lot of different assumptions that have been actually made even before we started. And some of the assumptions, like Nick started off talking about it, right? Homoscedasticity, and then it has to be linear. The data have to be independent. And then if you just start throwing in numbers, it's going to be it's going to be really biased. And has anybody used IBM Watson? I think it's a dangerous tool. I know I think they're working on it. It's basically it's an intelligent statistician, right? So somebody that can take my job away, basically. But it is a little dangerous because it has a lot of power. It can do a lot of different things, and the final conclusions can be biased because you need to really know what's going on in the back. If you don't know what's going on in the back, that's where the problem comes, right? The background of it, or what formulas it's using, what is it really doing, and everything else. So that's why I was kind of talking about the p-values and everything else. It uses heavily on it because I used it years ago. They gave us a copy of it just to kind of use it for in the academia. So I was kind of messing with it, and then I was with me and my few colleagues, but it was just a little, off. But I think they've probably come a long way after that. But I was. Yeah, maybe I can get in touch with one of the reps from IBM Watson. If we can get a copy of it, do you want to use it or? Okay, sure. Well, let me check with some people and we can see. Yeah, that's I think that's a cool software also in terms of where everything's heading towards. So basically, it can do everything by itself. Right, 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 exactly. Okay, now we come to the meat of it. So we took a little bit of stats, background. And then we looked at the history of everything else. Now we are looking at some of the statements that have been made lately by the American Statistical Society in terms of how to deal with data analysis. The first one is, what is a p-value? P-values can indicate how incompatible the data are with specified statistical model. That's all it says. So don't make conclusions based on that. P-value provides one approach to summarizing the incompatibility between a particular set of data and a proposed model for the data. So what is the proposed model? Earlier we saw that bell-shaped curve, right? The Z is the proposed model. So it has its own assumptions, it has its own mathematical formula, and it has its own probability calculator and everything else. So basically, you're comparing this with your data. That's it, to see if there's a good fit or not. So don't make final conclusions just based off of that. So the p-values do not measure the probability that studied hypothesis is true, which traditionally is what we've been doing all these years, or the probability that the data were produced by random chance alone. Scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. Okay? P-value or statistical significance does not measure the size of an effect or the importance of a result. By itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So, for now we know we don't really need to use p-values, and there's some of these articles that actually, so this article just came out. It talks about abandoning statistical significance. It just came out last month, and putting the p-values in its place. So there's been a lot of revolution on this. So now we know that our decisions should not be just based off of p-values. Okay, now we're going to concentrate on, I know everybody's been waiting for this slide, right? So what are some of the good statistical practices? Okay, let's start off with one thing. Don't rely on p-values for final conclusions. Rather, just use p-value as one piece of the puzzle. It's not bad to have a p-value, but just don't make conclusions based off of it. Use more than one statistical technique to validate results. What happens? Okay, next question will be, what happens if you use a different technique and you get a different answer? What do you do? Any suggestions? Okay. That's hacking. That's exactly what we were talking about not to do. Absolutely. So why are they different? So are we using the right approach? Maybe we're using the right approach, but why are they giving different results? So dig kind of deeper into it. And you dig deeper into it, you do your research, but be transparent, right? And you say, yes, this technique gave us this technique gave us this after everything else. Yes.
So what if we have multiple fields or variables, factors, and we're trying to determine significance of those to our hypothesis? What other techniques could we use to say that this particular thing?
Okay, that's an excellent question also. So, all right, so all the techniques that you've seen, which uses the p-values, right? So there are techniques that don't even use p-values. So those are exploratory approaches. So, you know, some of these approaches can be cluster analysis or just graphical methods of looking at your data, right? So use those techniques. So whenever you start using the inference-based techniques, which generate the p-values, also use other techniques like exploratory techniques just to see what happens. I'd say the first few steps are very critical. Cleaning the data. Your data is never clean. So there's different ways to clean your data. There are logical ways and there are statistical ways to clean your data. Okay? So it's like building a house. So start from the foundation. So the foundation is that. And then when you clean your data, there's outlier analysis. How do you perform your outlier analysis, right? And then do you have the right variables to go with it? And how much data do you really need and have in hand? So those are some of the things that you really have to keep in mind. And that's my next point. So perhaps use exploration techniques when possible. So initial data description and research question can drive the exploration technique. So when I say exploration, it only means just your basic descriptive statistics maybe, or graphical methods. And there are, of course, advanced graphical techniques in data mining and all that you could use these days, which are actually cool. So use those techniques also to see where you're heading towards in terms of analyzing your data itself. So, and this field is so broad, there's no like, okay, this is what you need to go here, make a right turn, make a left turn to get there, like I said earlier. So it really depends on what you have in hand. The data set, the research question, how the data looks like, and there's no one way to do it. That's exactly what I say. And every time I look at a data set, and especially since I work in the industry now, it's a completely different beast. And I work with a lot of DNA structured data now. They're really big data, and then they're actually usually wide data more than long. So there's more variables than there's more observations. So that's a totally different beast. And there's several different techniques to deal with it, right? So, and it doesn't stop there. So we're getting more and more and more and more techniques and information these days, right? So we need to pick the right ones. And the most important thing is another piece of puzzle called the effect sizes. So what is an effect size? So size of the effect. So in that case, in the regression analysis that Nick showed us, I think it was about 60% of the variation was explained by the model or something like that. So that can be one of the effect sizes. So when you do any sort of analysis, you will end up with an effect size, but most of the times you don't see that reported, which also need to be reported, which is really important. Okay, in terms of everybody knows what a correlation analysis is, right? So correlation coefficient ranges from -1 to +1, right? So -1 to +1. This is the easiest correlation or the effect size that you can think of. So do you know? Okay, your correlation analysis can also generate p-values. I think you've seen that on your software, right? Do you know what it's actually saying? This is what it's saying. So when you do your correlation analysis, your hypothesis is said to be there's no relationship between the two variables, right? So which means to say the correlation coefficient, I'm just going to say correlation coefficient, EFF, is equal to 0. That's your null hypothesis. That's exactly what you're testing, right? And then your alternative hypothesis is coefficient is not equal to 0. That's it. So when you test it and when you get a p-value of say 0.01, what are you going to say? When you compare with 0.05, significant. But yes, it's significant. It's only testing the fact that it's significant, but it is not saying by how much. That's why we have to look at the effect size. So effect size in that case, when you do this test, it might be only 0.15. The correlation coefficient might be 0.15. 0.15 is not really a high effect size, right? So there is a positive relationship between the two variables, but it's not really high. So another piece of the puzzle that's really important is the actual effect itself. So in regression analysis, we saw the coefficients. And I want to show you these right here. Actually, I think this is the right time. When you look at the model here, look at this. Weight is 0.01. It's actually really not a high effect size. I know the p-value is coming to significant, right? Where's the p-value?
But the 0.01 strikes me as actually a fairly large number. You multiply it by something big, by 220 pounds.
Right. But I mean, it really depends on what you're looking at in terms of like the effect, overall effect of how it's going to change. The overall model itself. Right? And then when you do, I think, yeah, that's where's that example you did when you predicted something? So, and also that's exactly why it's explaining about 0.64. What happens to the other 0.36%, right? So it's not explained yet by the two variables. So there might be other lurking variables and as such. So in regression, the effect sizes are going to be coefficients that you're going to look at. So yes, you have to look at the p-value, sure, and also always look at the coefficient. So every test you pretty much do will have some sort of effect size associated with it. That is another piece of puzzle. So, and also these effect sizes are all kind of point estimates. They're just estimates, right? They're just estimated. But the estimates can also, you can generate the confidence intervals. These are a little more, what do you say, technically a little crazy, but you can do that also. Be careful with the sample size in hand. This can drive your analysis. So, small data, large data, medium-sized data can run your analysis, and how many variables you have in hand. That's another thing to be really careful about. Okay? So the kind of statistical test you choose also can depend on the sample size of your data set and the number of variables you have. Okay? Especially when you're doing regression. Let's just say you had 30 variables as your predictors. So we can't just, and then for sure, one of the things that we saw in that example was multicollinearity. So multicollinearity is nothing but each of the variable, the relationship between the variables. The way it's calculated is just nothing but you just run a correlation analysis and it'll give you all the correlation coefficients. So all those 25 variables should not be used in the models. You have to be careful. So there are statistical ways to cut down or use the variables in the model that you want to use. Okay? So the number of variables also matter, along with the number of observations you have in your hand. All right. So dealing with missing values. So you deal with this all the time, right? In real world, data is never clean. And I have a theory on it. I think, at least me, I end up spending about 80% of my time cleaning up the data even before I start analyzing it, which is probably true. And you can probably think of it like that. So how would you deal with it? Are you just going to throw away missing values? What did you do before? Yeah. Right. You can impute them, meaning you can fill in those values if you wanted to. And there's a certain threshold for that also, right? So if it's more than 20% or something, you can't be imputing blah blah blah. So how would you deal with it? Would be if you have the resources. This is how I deal with it. You will run different analyses based on missingness and not missingness. Meaning you can fill in those values and then run the analysis and see what your results are. And you can delete them and run the analysis and see what your results are. Right? And if you get completely different results, you have to be transparent when you say, well, what happened? So you say, this is what I found with the missingness, this is what I found with the imputed values. Okay, so that's I think a good strategy to go. And then outlier analysis. And
I'm very curious about outlier analysis. I can deal with this in healthcare. So we're estimating the amount of claims, healthcare claims for an insurance company that we're going to see. And what you find is the vast majority of your data falls within predictable numbers. Then you have what are known as shock claims. So if someone goes into the intensive care unit for 30 days, it's a $500,000 claim.
Right.
And your average person is not going to apply 30 days in ICU. So the way that we handle shock claims
Okay.
in that situation, the particular threshold was set, maybe $50,000. Any claim over $50,000 was completely removed from the data set.
Because it's really extreme.
And so then we used the regular claims and did various techniques to predict what the regular claims were. And we took all the shock loss claims and a human used judgment to try to predict that. And I was always a little bit uncomfortable with that method. The human judgment I was kind of iffy on, but the idea of removing those from the base data set, I really debated if that was good.
That's an excellent question when it comes to outlier analysis. It's not an easy solution. So what you could do. So what you're talking about is when an outlier is a true outlier. It really is. Sometimes it's not. Sometimes it's just a value, right? So what you could do is you can analyze the data by clusters. Meaning, say whatever, it's 50,000, right? So all the values that are close to 50,000, let's just say, take all the observations from $30,000 to $50,000. Take those by itself and take the other ones. So basically break it down by clusters and then analyze it. So each one will have their own models. So the way some of these models are set up are not going to be able to handle some of these outliers because one outlier can throw everything off. So one of the strategies is you could use clusters of observations, take them out, and then run them by like that instead of actually throwing it out. In that case, you would have used the data points and not excluded from your data set because there is some valuable information there also. So that's one of the strategies that you could probably use.
Maybe it's not, it seems unlikely, right, that insurance claims are normally,
They are much smoother than you expect.
except when they're not, right? I mean, I guess the question is it an outlier?
At large scale, it starts to not become an outlier.
Yeah.
But at a reasonable size like Birmingham, it is an outlier.
Yeah.
If you want to take into account Alabama, then you move from 50,000 to 150,000. If you want to take into account, I've played with a lot with the Walmart account. You can imagine the number of employees that Walmart has, and then you almost get to the point where you can ignore it and include the outliers at that point. It just depends on the data set.
Yeah, it depends on the data set. And yeah, outlier analysis it's a whole world by itself also. Running models based on outliers is another strategy. So with and without outliers, what happens? The entire data set and cluster it and see what happens. I know this takes a little bit of resources. Sometimes you might not have the resources to do it, but to be in an ideal world, that's what you probably want to do. And report confidence intervals. And then we talked a little bit about compatibility intervals. So which means to say, when you take the confidence intervals like this, again, so there's a whole range of point estimates here that go from 15.5, 15.6. So you use those ranges to come up with your p-values or whatever, or other effect sizes and everything else. Okay, another thing that most people don't do is something called multiple testing. So when you have, this is a whole different concept. When you have several different hypotheses on the same data set, for example, again, multiple regression, we had only 3 individual variables that went in the model. Let's just say you had 25. They need to be adjusted for p-values to get the actual p-value. So whatever p-values that we saw in the Excel are not really the actual p-values. So whenever you have more variables, it need to be adjusted. That's one of the key components to it. And then lastly, be transparent about the entire statistical analysis. So that's one part that I don't see in most of the studies or most of the articles that I read. And all of a sudden, you see these claims. I'm like, I'm not seeing where this is coming from. Tell me the full story. So if you cannot skip steps when you're running analysis, or especially when you're writing it up. So be transparent on every single step that you've taken to come to the conclusion. When you skip something, so it's like telling a full story. It's like watching a movie. All of a sudden this happens, but hey, how did that happen? That part, I don't know, right? So when you're making your conclusions, just really make sure to kind of be transparent about everything else.
How do you, that's a great question right there. How do you present your data in situations like that? I have found that even my manager, but absolutely an executive, has no interest and no understanding about statistics and heavy data analysis techniques. So I've always really very dramatically dumbed down my end conclusion. You know, even having, you have a rating up there of 15.5 to 16.5, you know, that's almost shady whether or not put something that variable in front of an executive. How do you show this transparency, show this uncertainty, while still keeping your presentation very clean and easy to understand?
Okay, so I'd say when you're doing the analysis, make sure to cover all the bases. Okay, so say for example, of course you cannot put every analysis that you did, and you might have different conclusions. Maybe conclusions are slightly off, but finally you're the one who's going to make the decision on which one to actually. Okay, this is the one that I want to present. But in case, of course, they don't want to see what all you've done. But in case there might be a question to where, hey, how did you get there? So you have the full story in the back when you got there, right? So you're making logical decisions step by step by step instead of just going one route. Or somebody might ask you, hey, why didn't you do this technique? Or why did you leave this variable out? Or why did you do this particular kind of outlier analysis? You should be able to say that. And I usually always have that in my last slide, something like, any more information, like, there's a folder that I usually put all the stuff in. Like, go to that folder and see it if you want to see it. I work a lot with the pharmaceutical companies. So most of our clients are pharmaceutical companies. And sometimes they want to know everything. They have their own team of people they're looking at. So our team, we work on some stuff, but whatever we do, we have a step by step like code and everything else. And also so that if they want to replicate our study, they should be able to. And then final conclusions are not just based off like whatever we thought the right thing was. Yes, and then like I said, so this is a logical step to do. Yes, yes, no, yes, no. We did all this. Finally came to this. That's it. Oops. All right. I think I had an example right here. Nick, would you mind helping me with this? Sure. This is probably kind of cool example that I have. Okay. This is a real world example. This is people on Titanic. Everybody knows. I think everybody knows Titanic, right? All right, so we have their actual names, and I use this in my class. And we have passenger IDs, and when we have the fact that if they survived or if they died, and we have their class, first class, second class, third class. So what would you expect? People, and we've watched the movie and we've read the books, I guess, right? People first class, they survive more than second and third class. And then we have gender, and then we have their age, and then where they boarded, and of course fare. So what I want to look at is, we probably know this answer already, right? What happens for people who paid? Oh, is there a difference in survival based on fare? Those are all in pounds. What do you think? Absolutely, right? So we all know people that paid more money probably survived than people who paid less money. So let's do a quick fare for people who survive, just the average fare for yes versus no. Okay, so
Relatively new formula, yeah.
Yes, it is.
he's an Excel expert.
I think it came out last year.
That's correct.
Okay, so we're actually running an inference-based test called the t-test, right? So who made the t-test? Student t-test, the guy who ran the brewery, Gossett, right? So here is something that, okay, so the hypothesis, this is a different test. So this has a hypothesis by itself. So the hypothesis here is, null hypothesis is the fact that there's no difference between people, no difference in fare between people who survived versus people who didn't survive, right? So that case, so it's going to be survival fare, right? Yes, is equal to survival fare no. That's your null hypothesis. And then the alternative hypothesis is exactly going to be different. So we got 48 and 22?
Yeah.
So people are, oh my God, that's a huge difference. So going back to the last slides to be some of the things to consider here is, and of course we can, let's run a t-test also. Let's go back to the data. It's in the data tool.
We can run it.
Yeah.
We can do it that way.
Yeah, we can do the t. It's just going to give us the.
Can we do it as is, or do I need to switch survive to yes?
Yeah. So I think it's best to use the data tab.
Well, what I'm thinking is I need to move survive to a 1-0.
Oh, I don't know about that. I think it deals with it. So this is what we call a t-test, right? So you're comparing two different groups. The two different groups here is people survived versus people didn't survive, and then we already know the answer to it. Meaning, what, 48 pounds versus 22 pounds, and there is a difference between the two. So what is your p-value going to be? It's going to be small, correct? Because you're going to reject the fact that the fares between people who survive and people who didn't survive is the same. It's going to be different. So you're going to reject. So just by looking at so that's your first step, is what I was trying to say. So the point was, when you just look at the means by itself, just the averages, you'll already know what it is. So you need to definitely report that instead of just the p-value, right? I think it had the p. Okay. So, and then the effect size can be looked as the difference between the means. 48 versus minus 22, right? So you can look at that, and then you can also report the standard deviation to go with it. And once he does the t-test, it's also going to give you the. There we go. That'll do. Yep. Yep, fair. As you can see, look at this. It's a really, really small p-value, which we already knew that, right? So when you're doing a test like this, just don't look at the p-values, but also look at the mean difference between them. The mean difference was just this, subtracting 40, what was that? 22 minus whatever that was. Yeah, 48 minus 22. So that's good. That's the effect you already know. And then yeah, p-values, the next puzzle, one of the puzzles. And there's something also known as a statistical effect size, which we're not going to get into, but it's called something called a D statistic that you can look at, and it's going to give you if it's a low, medium, or high effect size. Okay, and then of course the test will also give you the point estimates of the confidence intervals. So when you're doing any kind of test, the point is to actually look at everything to make your decision, and not just based off of just your hypothesis testing. That's it. Questions?
The statistical maybe one more time. The adjusted R squared is very low. Have you seen that? R squared and the adjusted R squared number. Why is that?
So here we're trying to predict it. So it's not, we need to do the t-test. Yeah, lots of other things to go with it. So if you do the t-test, so it's not a good predictive model. It's not a good way to predict it, but we're trying to see the difference between the means. Yep, I think there should be. And I think it should be, let's go down. Yep, equal variances, two sample assuming equal variances. That one. Yep, that one's the right way to do it. So now you'll see everything else. I think it should also give you the effect sizes. Okay, I think you should just put the, yes. Or you should just put the fares for S and fares for no. Right.
So we're going to go right there. Oh, I see what you're saying.
Yeah. Yep. Just the fares for S and fares for no. You can tell he uses Excel for everything. It's like boom, boom. Any questions?
So we're asking, are these numbers really different?
Yeah. Basically. And then sometimes what p-value will give you is, even if it's a close difference, it'll still give you a significance. So that's exactly not what we're going to go after. Yep, there we go. That's it. It gives you the number of observations. Yep, even gives you the hypothesis mean difference. That's exactly what I wrote on the
variance on there is vastly different. So do we need to use the other t-test where there was, okay.
It should be okay. And where is the p-value? Two-tail, yep, right here. One-tail, two-tail, both.
But I have a question about the one-tail versus two-tail. So we use the two-tail when you know that, okay, your distribution can be in the both sides.
Right.
Sometimes I can play with that because I know that, okay, I'm thinking that, okay, if I use this drug, the result will be good.
All right.
Okay, that's what, for example, I know already I have the previous background. I did the animal study. It is a good cancer drug. It kills the cells in the petri dish and the animal. Okay? So I can use one tail, and it gives me a really good p-value, and I can publish it or get a grant. And so how I will.
That's exactly.
What they will do. It's very easy to sell. I mean, everyone wants to sell and get a grant, right? So how you're talking about the clarity and the honesty and everything. Right? At the end of the day, it's a money chase, and you want your grant to be the help. As an auditor, I can tell that, okay, I will give all the confidence interval about this and that, but then when I will go for a grant, and I have seen that many of them kind of we took care of.
Yeah. Okay, so what I would do is this. So when you're doing the study, you're setting your hypothesis first, right? So based on what I hear is, if you set it up to where your population or whatever is greater than or equal to versus just equal to matters. If you're going after, so the earlier example that I was talking about was the chip factory, right? So from the FDA's perspective, all the FDA cares was if it's greater than or equal to 16 ounces. Yeah, it's on the one tail in that case. But if you want exactly to be that number, it's a different story. So it really depends on what you have in hand. And yes, I agree, maybe some situations call for maybe one side versus two sides. When you're doing the power calculations for the sample sizes, right, when you're writing a grant, that's one thing you got to do, right? So you have to talk about both. So meaning you require so much sample size for one-sided, and then you need so much sample size for two-sided. End of the day, you're trying to get money, right? But I would write it like that. That will make it a little bit more clear, at least, to see what's going on there. Any other questions? Oh, hopefully this was educational.
It's good to just hear these words again every time to time. You take a statistics class, and it's like, okay, cool, yeah, and then you go, forget everything.
Yeah.
Someone has to remind you. So
Good.
Super helpful. Yeah.
I actually want to go back to school and statistics and become a data scientist, but someone programmed BlackRock on Wall Street. How often is institutions wrong statistics?
There's lies. Well, you see, how often can a statistician be wrong?
On Wall Street, not very often.
So I mean, every time I try to gamble, I don't win. So I mean, it's all probability. It's a game. So I don't trust myself going and gambling. So I don't gamble. Or I invest in stocks a little bit, but I'm not going to put my life on it. So there's one saying though, a model is a good model if it just gives you enough information. There's never a perfect model. That's it. So this gives you information about something. I think the sports analytics is going to be really interesting because I have done a little bit of work on that kind of data sets. But yeah, it's going to be something interesting to just see how they do things. And most of my work lately have been in terms of using big data mining, doing predictive models on cancer treatments. That's what we do. So it's gonna, or comparing drugs, chemotherapy drugs, in terms of which is doing better and stuff like that. So, like I said, the field is ever growing, and it's getting a little dangerous, a little bit, because everybody's a data scientist, which is good. It's like I call this the IT back when IT was growing. So I think there's a lot of room to it, but yeah, it's a very interesting, very fast growing field, and I kind of try to keep up with it as much as possible. And some of the trends that I'm having to actually change a lot of things that I did in the past differently. I'm changing a lot of it now, and with the software and everything else. My primary software, I use SAS and R both. Sometimes I can get some stuff in SAS that have it in R, so I go back and forth with it. But things are changing rapidly. I know that much.
Hypothetical question: do you think that in the future the statistician's role is going to be down if, for example, neural network, RNN, and these things are coming out? Okay, so neural network and everything, if just it's taking all the features and everything by itself. Like you don't need to choose the features by seeing and everything, and neural network do it by yourself. Go back and forth, right? So where the statistician's role would be at that time?
Statisticians' roles are always going to be what neural network method, how to feed it, is what's the computer probably can do. So it's like asking this question: are we all going to still keep driving, or is it all going to be automated?
Automated.
It's all going to be automated, right? Are we at a point to where the automation is going to make ethical decisions? It'll make a decision. So, so it's like one of those things I was reading was what the car cannot do yet is, yes, it drives automatically, but if you're driving, you're sitting behind the wheel, and somebody's walking, regular person, it'll stop. What if the person who's walking is crippled or has, 2 bottles of whiskey in their hand or something and walking? It's going to still do the same thing it's supposed to do still. So there's a lot of things to it, but statisticians' roles are still going to be in terms of getting the right techniques, I think. And when I started this field, I was one of the early graduates in the whole data mining world, and I thought it was just interesting. So back in early or late 2000s, 2009, 2010, that's when it kind of kicked off. And I don't know what got me into it, but I was already there. And then it really, really kicked off after that. But like I said, the field is ever growing, and statisticians are the one who are coming up with newer techniques, and they're teaming up with computer science engineers, right? So that's the AI world of it. So, any other questions? Okay, good. Well, thank you. I'm glad to do this, and I haven't done this because usually my audiences are